Hello.
Hi there. Okay, so I simplified this to not show the intermediate labels here,
Okay.
but I'm trying to display this in a way that's even vaguely comprehensible. I mean, essentially what this is doing, so if I just write something very straightforward here, let's say I write like S of S of S of S of S. Okay, I don't even understand the first thing. So this is S of S of S. I don't know why. Do you understand what this is?
Let's see.
But why are these things indicated in a different color than the other things?
Oh, because they're about to be replaced.
Okay, fine.
Well, if you want to simplify this, first thing to do would be to delete expressions which are not used anymore, which then apply to this state. I mean, this one is actually pretty simple to understand.
Okay, well, let me look at this state, and then I'm going to look at the corresponding state where it's left associated, okay? So S of S of S of S of S.
Yeah, so here it goes to S from the second position in each hyperedge because it's a root, it's a head now.
What does each hyperedge represent? And by the way, where was our previous stuff with the when we were previously trying to look at these generalized combinators? Do you remember where that is?
Well, the previous code didn't work at all for fundamental reasons.
But I had a visualization of at least I had a visualization of a combinator shown as a hypergraph. See what I'm saying? So this
is doing it as well.
Okay, so if I go here and I say all combinators of 3, for example, and then what is this thing actually going to generate? Is this going to generate, do I have to say Wolfram model plot on this thing?
Yes.
Okay, and then I also need this ridiculous piece of hackery here.
I don't understand. How does it even work? They're both symbols.
Read the code.
Oh, I see. So if you have KK instead of K, it's not going to work anymore.
That's right.
Okay.
I just said it was a piece of hackery. What the hell? Oh, I forgot the expression to hypergraph, comma root. Okay, so these are the graphs. And actually what I probably want to do here is just say, all right, do I understand this? Explain the pieces to me. So I'm using.
So the hyperedges correspond to expressions. So the one on the right is S of S. Because, so hyperedge has 3 vertices. The first one is just the label of that expression. The second one is a head. The third one is an argument. So the one on the right is S of S, because both the head and the argument go to S.
I understand. So the basic idea is each ternary hyperedge has the expression label head pointer and argument pointer.
Right.
Okay. So now why does it need the expr label?
Well, because another expression needs to be able to point to it.
But why doesn't it just point at its head? Why doesn't it just point at this thing here, this node here?
Well, maybe it can.
Okay.
I'm not sure.
I think that makes more sense. Can we just try modifying that code, the expr to hypergraph, just to see what it looks like?
Okay, well, one problem is that then the edges that go from pointer to expression would be binary edges as well. So those two types of edges are going to be confused.
I see. But we could just have a self loop. Every head could get festooned with a self loop. That's analog of bracket.
We can.
Right, alternative approach. Indicate each head element by a self loop and have only head arg. So I'm trying to understand the generalization of all this into, instead of just a head and argument, what if each individual, so wait a minute. So the connectivity here where is the tree for connectivity? These things are not arbitrary hypergraphs, right? They're hypergraphs that are constrained to have a tree-like structure.
Yeah. Well, more or less. So the way it works is that in a fully expanded form, it's a tree-like structure, except it might point multiple times to K and S.
No, I understand that. These are not
But
general.
In intermediate steps, it might get compressed because you might have two pointers pointing the same expression. Because, for example, the rule for S has Z twice. So there's a special rule which uncompresses it. So it takes this double point, two pointers pointing the same expression, it duplicates this expression, and it propagates it to the entire hypergraph.
Okay, hold on. These are not general hypergraphs. They are ones generated to reflect tree structure, and any shared subtree. I don't understand why it has to break off the shared subtree. If it evaluated one way,
because Wolfram model rules cannot match the same expression twice.
I see. Because isn't that a foliation issue? I mean,
no, it's a rule matching algorithm issue. Because if you have say you have a large combinator input in the rule, and then it happens to have the same tree appearing twice in different places.
Yes.
And it should be able to recognize both the case in a hypergraph where those subtrees are separate and in the same place. But it has to match different expression to every expression in the input rule, given how it's set up right now.
Okay, wait a minute. Has to be duplicated because of the current setup. Okay, but what is the generalization of combinators? I mean, so you know, combinators are tree structures, are tree rewrites. What is the appropriate generalization of combinators to the general case? See what I'm asking? Max, do you understand what I'm asking? So I'm asking.
Yeah, well, it's. I mean, I would argue hypergraphs are generalization in some sense.
No, I think that's right. I think it's right. I think that is the correct answer. But I'm trying to
just
understand.
they need to have some optimizations to be a real optimization without any loss.
Hold on though. Hold on.
I mean, not regeneralization without any loss. Yeah.
No, I understand. But so there's in here. There's labeling I don't understand. I mean, there are these special elements which are, in a sense, there's combinators without names. I mean, if I removed, so the nodes that don't have names here, right, there's a special root vertex and there's special named sink vertices, so to speak, leaf vertices.
Yeah.
Okay. Well, I mean, I'm still puzzling about how do I see the tree structure of the combinator in here? Do you see what I'm asking? So
yeah,
like for instance, okay, so let's say I say nest list S
well,
kernel.
if you convert it into a graph and then do layout.
Well, I tried that.
How
That's
do
what I
you see
failed
it?
to do. That's what I failed up here to do. See this? Layer digraph embedding with an S and a K there. Did you see that?
Well, you cannot, Wolfram model plot doesn't support it. So you
Doesn't
have to
support the
convert
graph
it to a
layer?
graph. Yeah.
Why doesn't it? Oh, because it doesn't know how to deal with. Okay. Well, so here, so expression to hypergraph, but then from that we want to say hypergraph to graph, right?
Yeah.
What's this?
I'm not sure. I
Oh,
think that's about vertex labels.
what the hell is that doing there? X semicolon and then that. know what this is doing. Why is that jumping in that weird way? What is this doing? Why is this doing this? I don't understand. Do you understand why it's doing this?
Not really.
What is going on? What is going on here?
What if you just plot one of them?
Okay, what is going on here?
Can you just do resource function of hypergraph to graph of the argument
Actually,
without?
I'm going to just send this in as a bug.
I'm just wondering if it's a bug in the resource function. Oh, that seems weird this way.
Oh my God, when I copy paste, it's doing me the wrong thing. How could it be a bug in the resource function? What does it have in it?
Some weird graph options.
Let's just ask for options of this. I don't have time to debug this right now. Graph layout, arrow dimension, arrow 2? What the hell's that? What do you think that is?
Well, I guess it's kind of an automatic. I've never seen it before.
This is very annoying. Okay,
well,
but
that's why we need CI.
Bullshit. That's not going to solve this problem.
Why not? It can be automatically tested.
It's not. We've got automated tests. They don't catch this because this is something that is a complicated thing that has to do with the rendering on the screen. And, you know, we built for 30 years, we've built tests that do testing of that type of thing. It won't catch all cases. That's what's going wrong here. This is not a failure of testing. And anyway, look, it might already been caught in a test because I'm running 12.2, right? But in general, it's either catchable, in which case we're catching it, or it isn't catchable, which is what I suspect is more likely, that it's some kind of thing that has to do with the way the rendering works, and that the automated test will just show this up as fine. Anyway, let's not discuss that. Let's look at this thing, okay? So I don't understand this picture. S of S of S. Okay, so this is coming down here. I don't understand this. And it doesn't help there's a graph rather than a hypergraph.
Yeah, it's kind of harder to understand now. I mean, I can understand it, but it's not trivial. The triangle on the right has to do, well, that's the entire expression. And then the curved edge together with two ones below, that's S of S, which is the head.
You stop it there.
Yeah.
It's weird. It dropped
It
out.
just disappeared.
Yeah, well, we reappeared. Okay. Look, I don't understand. Okay, anyway, I got to go work on some other stuff, but I don't understand that there are a couple of things here. So I understand how this is making trees specially. Then I want to understand how you generalize this to, instead of having trees, have it be hypergraphs. But the trees are made by having, in these pictures here, right? What's really weird is that every leaf comes back to the same thing. Do you understand what I'm saying?
Yeah. Well, it doesn't have to be. They can just be labeled and be different vertices.
Is that going to work?
Well, no.
Well, then it's not going to work, is it? Right. So we have to. So in this concept, they all have.
We can draw it like this. We just
no, I don't care how we draw it. I don't care. Yes, but what we care about is how the thing evolves, because that's what's determining. We should draw out the rules. I see. The rules don't care that all those leaves come back to the same thing. Is that a true statement?
Yeah.
No,
they just care. It says.
They do care.
Well, they care about the label.
Yeah, they care. Every single rule has to consult the master S element to know what to do. Yeah. Right? The rules can't be local.
Well, what do you mean? We can make S local by representing with some structure in a hypergraph.
No. That's not what I mean. What I mean is that at every point, right, everything, there has to be this giant thing that is going back to S, so that S directly connects at distance 1 to every element here. Right, in the pure S object. Okay?
Okay.
I don't know why it goes like that, but anyway. Okay, so what I'm saying is, as we make this bigger, right?
Right.
This will always have an S at the middle. So an S has to be distance 1 or 2 from everything, right? It's got to be a big...
But not everything. I mean, if...
Almost everything. Almost everything. If it's a pure S, a nested S expression, S has to be within distance 1 or 2 of everything, doesn't it?
I don't think so, because heads and arguments can be nested themselves. And if they're nested many times, you could have distance more than 2.
Okay, so let's look at one of those. Okay, so you're saying, where do we have that? Here we go. So in this case, you're saying that if we say here, nest list SS5. Okay, so this is a case where we have S of S of S of S of S of S.
No, it's more complicated because the heads needs to be nested as well.
No, I understand. I understand. This is right nesting. What we need is left nesting. How do you do left nesting? You just have to say nest list of hash of, instead of S of hash, I think it's hash of S, isn't it? Yes, it's that.
Yeah.
No, yes, right. Okay, so then here, okay, it's still distance 1. Everything's
Yeah,
distance.
because you need both.
Both what?
Both types of nesting.
Okay, so let's try doing nest this S of this thing.
Wait, maybe it's hash of hash. That might do it.
Well, it's going to get exponentially bigger.
Yes. Right, so if you look at the very right of the last element here, it's pretty far from S.
Right, because those are sub-expressions. But if I look at this thing here, and I say, it's a pure tree like that.
Right.
Whereas this thing here,
well, we can represent S with a self loop or something. That would make it look like a tree, and it will probably make evolution faster as well.
all right, then let's do it. And let's do only the ones with pure S's. We don't need to do,
Okay.
we don't need to worry about the case where there's both S and K. All right, how will we do that? Is that easy to do? I think you have to change the code. I don't think. Do you want to just try and change the code for a minute?
Okay.
Meanwhile, let me work on something different for a second.
I sent you the localized rules.
Okay, hold on 1 second here. Is this obvious that the number of matches is related to
Related to what?
the number of leaves? It's not quite the same.
Yeah, it's not obvious. Well, I guess matches require at least one leaf, or maybe they're in the rule. But they would, some of them would overlap.
But so I'm trying to understand how you'd make a causal graph out of this thing. Because the evaluation order that I'm using only does one update at a time. But if you did multiple updates at a time, you could make a more complicated causal graph.
Why would causal graph depend on it?
It's not a multi-way causal graph. It's just a causal graph of in a particular foliation, right?
Right.
So it's just saying I mean, we know the thing is causal invariant. I see. So that's an argument why it shouldn't matter what the updating order is. What the heck is the causal graph of this thing?
Wait, do we know that it's causal invariant?
Yes, we do. It's the nature of combinators.
Because it's non-overlapping.
Yes. The proof is actually supposedly slightly non-trivial. It's because a tree can't, it either has to be a subtree. Yeah, I think that's right. Anyway, so let's look at you just send me an email with the thing here.
Yeah. Well, it's if non-overlapping, it's not just causal invariant, it's a single way system. So then there is only one causal graph.
No, because, well, yes, maybe, but then how do we compute the causal graph? Okay, hold on, let's look at this first. Okay, so what did you do at the end here? Did you add
So there
something?
is few new functions.
Where
so
are
there's
they?
localize S, which takes a state and, well, turns S to unary edges.
Let me just put this in the right place.
Well, you can make causal graphs in the emulated system, which I guess would look similar.
Hold on. Okay, so what should we call this? What is the section? This is
Localization.
I see localized localized combinator literals, so to speak, combinator literals.
Yeah, well, it's only S at this point.
Okay. Okay. So now, what's this doing? So where's the S? The S, oh, there isn't an S. So it's
Yes,
better to not.
S is a unary H.
Right, so why are there sub pieces here? What's happened here?
Because it's not garbage collected. So the root is on the second one. It's highlighted in red in the middle.
Okay, but I don't want to see the final state plot. I want to see the thing build up. And I also don't want to see, I mean, I don't think it's useful to see all the labels of those intermediate things, right?
Yeah.
So other than the root, I don't think we need to see the labels of anything. I think we just say vertex labels are unknown.
Yeah, that's true. The root is highlighted already anyway.
Okay. Okay, well, let's still go back to my original thing here, where I just want to do expression. Is this expression to hypergraph going to work? What is the new version of expression to hypergraph?
You just, yeah. You cannot convert it back from hypergraph to expression.
Okay, so I just want to show, I guess I can say, can I say Wolfram model plot here?
Yes. Well, that's a default, but you need to say graph highlight goes to root. Least to root.
Okay. Okay, let's see if I understand this. Okay, so that's the root at the end there. And this is saying, which way round do I read this? Do I go from the root? Oh, I see,
It's
the root.
head and then the argument. So the head is a whole sub-expression on the left, and the argument is just S.
Okay, whereas this will be the opposite way around. No, it won't. This particular one is S of S of S of S.
Right.
Okay. Can we evolve these puppies?
Yes.
That's what you did before. Okay, I mean, there's not a completely stupid way to visualize these things. We need the hypergraph to visualize it, right? We can't do this with just a pure graph.
Well, not in a lossless way.
What do you mean by lossless? I mean, in other words, to show something where we can uniquely go back from the graph.
Yeah, I mean, we can make graph out of a hypergraph, but it wouldn't be any simpler.
I understand that. I understand that. So in principle, we could have S being a single self loop and K being a double self loop or something.
Yeah.
Okay, let's see the evolution of one of these guys. Okay, so you say this is the evolution. So let's look at the evolution of one of the ones that doesn't stabilize. Like that guy there. Oh, come on. Okay, how do we garbage collect? So by the way, why does it generate garbage?
Well, because if it, let's see. Well, because if there's sub-expressions that are not used anymore, it cannot just delete them all in one event.
So a sub-expression that isn't used. How can there be a sub-expression with S alone? How can there be a sub-expression that isn't used?
Well, the rules are the same, so they need to support case as well. But also,
there's no K in action here.
It needs to repeat expressions on the left-hand side of the rule on the right, because if it didn't yet duplicate expressions, and then there might be sub-expression that would be used in different parts of the expression. And then if it doesn't duplicate it after it applies the rule, then it would break the other one, which means it has to preserve sub-expressions after applying the rule.
Right,
and that's why even in S case it's still here. Well, we just need, well, what we need is hypergraph connected components, and then we need to find the one with root in it.
Yeah, I know. What the hell is that? What on earth is that creature? Do you think that is a meaningful causal graph?
I wonder what is that highway in the middle? You can use layered causal graph.
I think this is useful. I don't really understand what it means, but let's try one that has more straightforward behavior. Let me try. Let's try this puppy just for fun. I think this is interesting. I don't really understand what it means yet, but I think it's interesting. Let me see. Is there a more straightforward? So each event here
There are actually three kinds of events. There is evolution event, means combinator evolution event, and there's duplication of sub-expression and duplication of SS, which are different rules.
That's bad. Could we indicate those different events? Could we prune this for only the combinator evaluation events?
Let's see, pruned in what way?
Well, combinator evaluation events and S duplication and sub-expression duplication.
Well, we can color them.
Yeah, is that easy to do?
Well, more or less. So you can get indices. So vertex names are just event indices, and you can get a list of rule indices for all of them.
You just write code that does it and tell me what to do.
Okay, well, I actually do have code already. Okay, this is a code. You just need to add an extra color.
What's this? I don't understand what this is. Is this the rule for these combinators? I hardly think so.
No, just a run example. So you need to replace it with evolution.
Okay, but then this here with the actual evolution. So for example, if I do this one here.
Yeah.
With the layered causal graph or not?
No, just evolution. Right, and then add another color. So it says one goes to black, two goes to white. Third one.
Can I do vertex size goes to something bigger?
Sure. Well, just ordinary graph.
Oh, vertex size goes to 2 or something. 1. All right, so which color is which?
I see one. So wait, really? Hold on, can you do rules? So for this evolution object, just use rules property. So we know which one is which. So it's actually hard to understand. Well, no, the first one is the evolution rule. And the other two are duplication. So the black one is the evolution rule. So that's what the highways are for. I see.
Okay.
Well, there are a lot more duplication events than evolution events.
Welcome to the world of space. It's a lot more effort spent in the maintenance of space than anything that happens in space. Okay, so I have a question here. If we are thinking about actually, I should just make another one of these. If we're just imagining, so let me just make a thing here. Okay, if I just wanted to make a regular causal graph from one of these puppies, what would I do? So in other words, if I just take this thing and I say SK outer evolve list of this, comma 5 or something, I get all these things, right? How do I make a causal graph that shows what's going on in these things? Do you see what I'm asking?
Yes. Well, I think we need to make expression events graph first, because it's easier to understand.
Okay. But so from that, for that, what we need to do is in here, I've got something that says in here I say first of sort by. That's the that's this SK step. Okay. So here, so that's the thing that just generates a single step, and this is doing the event selection here. See what I'm saying?
Okay.
All right. So the question then is,
well, we need to figure out what are the expressions.
Yeah, but
I imagine
step,
expressions that would be defined the same way as an emulation. So that, you know, each sub-expression at each level is expression.
Sub-expression at each level. So this is well, actually, if I just say combinator tree of this, okay, that's the tree representation of that for what it's worth. Now, what are you suggesting?
Yeah, so I guess each vertex here would be an expression events graph. And so each event deletes some expressions and produces some expressions.
So each event is a mapping from graph to graph. So I mean, in other words, if I say nest list of SK step, comma, this thing, comma 5, and then I say combinator tree on that, then what you're saying is that the causal graph is telling us how to map. It's telling us which of these nodes maps to which other node here.
Well, nodes here are expressions in the expression events graph. And then each event takes some expressions as an input and creates some other expressions. And we know which events are causally related by looking at which expressions are common to them. In other words, if one
I
event,
understand, but I mean, so the S will pick up 3 nodes here, right?
Right. But it's not that simple, because there are common sub-expressions we need to think about. The S rule in particular, it has Z in 2 places. which means it creates that different ways one can think about it. One way is that it creates a whole new subtree, which means a lot of things are going to depend on this event, everything that happens in that subtree. Another way of thinking about it is saying that it's the same subtree.
Right.
But
Create
then
two copies of Z, of the Z subtree.
Right, but if it's the same subtree, then we need to deduplicate expressions, which is a tricky business on its own.
Okay, so hold on. Let's just think about this for a second. So this is saying, because what we're trying to do is we're trying to say, I see. You're saying if everything depends on that, everything in that subtree will have a giant dependency explosion. Right?
Yeah, but I don't think it's the right way to think about it, because this event doesn't really create the subtree.
No.
It just references it twice.
Right.
And so what we really need is expressions deduplication.
Okay, so this should be the same subtree. Gets a dependency explosion. Okay.
But the problem is that if it's the same subtree, can't it be matched in different ways depending on what references it? Probably can be. If we have a rule which is one level deep into the subtree, but it has different stuff above, and so this rule will now match this rule will now overlap the same subtree in different ways.
Yes.
Which means it becomes a multi-way system.
Well, I know it becomes a multi-way system. I mean, we're just picking a particular, I mean, there is a multi-way system here.
Well, not if we duplicate subtrees.
No, I understand that, but I'm talking about a particular event selection function here, because we're trying to get a single causal graph out of this, which we know is going to be the same causal graph, independent of how we do this, because that's the non-trivial
Selection or ordering function.
Selection event ordering function.
I mean, they're different things. Selection function is deciding if two events overlap, you decide which one you want to use. The ordering function is just you have a bunch of events, they might overlap or not, and you just pick in one of those. If events don't overlap, there's no selection because you can use both of them. So you don't need to select between them.
I understand.
But I'm saying if we deduplicate common subtrees, then it does become a selection function. Because the same event might use a part of the same subtree in different way.
Hold on, I want to make one picture here. So this is the steps. So for each step here, I want to be able to say map at a framed of this. I think I don't even need to do that. I think I just say, does position do framed, do heads to true by default? I think it does. Okay, so now I'm doing this. Okay, that's actually useful. That shows the matches. You see what I'm saying? That's the possible matches.
Okay. Let's see
But
how
really,
can
it
we even
should
tell if they
highlight.
overlap or not.
Well, these ones overlap because they're inside each other.
I'm not sure about it because, well, one can be at the top of the tree and the other one at the bottom of the tree. That doesn't mean they overlap.
So in each of these boxes, really, I should be separating out the x blank, the x blank, y blank, z blank.
Yeah. Right, and then as long as you don't have exactly the same box appearing twice, they don't overlap.
Okay, can we write the little piece of code that puts these things in separate boxes? So what we want to do there is, this is the position. So instead of just doing framed, what we want to do is we want to take that and we want to say sk box of xbar colon equals. So now this assumes, actually what we want to say is sk box of s of x blank, y blank, z blank is, now what we want to do is we want to, so we could just say grid of, can we do that? Yes, we can do this. We can do this. We can just say grid of S, how should we say, row of S, X, Y, Z, framed, frame arrow, true, all. Okay, and now we say SK box of K, okay, so I claim what we do here is we say in this, we say SK box I may have to say grid here. So what the hell is that S of S doing there?
Why do you have a Z in the K case? You have X to Z in the second box.
Okay. Yeah, but more seriously, why am I not seeing that? Why is that S? What's that SS doing there? The heck is this? That's an SSK.
We need to evaluate the first SK box.
Okay, and now for this, to make it a little bit clearer, we will put this here. I really want to, do you know how to use the background option?
But not in non-trivial way.
magnificorial. Actually, I don't want white. I want very light gray. I want gray level 0.9. Actually, no, let me make it light yellow. No, actually, what I want to do is I want to say lighter of red, comma, 0.8. So that becomes sort of a pinkish thing. Okay, now for this, okay. And now let me just.
Well, the same boxes don't appear twice.
That's actually a pretty good visualization of this.
It kind of explains why.
Why what?
Why they don't appear twice.
Hold on, let's just try running it a few more steps. What do you mean by the same box doesn't appear twice? You mean that whether the S has an S nested inside it?
No, they're the same boxes simultaneously red and blue, or red in two different ways.
Because this is just doing leftmost outermost evaluation, I think.
But it's doing all possible evaluation. I mean, so there's all possible matches.
Oh, but it only uses one of those matches. Oh, you know what? I didn't indicate a very important thing here. This is all the possible matches. This is all possible matches, right? Right, and then what we need to do is to show which match is the actual match used, right? So the actual match is going to be, okay, so I think the actual match is always going to be the outermost one of these, but let's actually look at that. Okay, so then what we want to do is we want to say to this, we want to do a further map at. Actually, if what we do is we do a sort by here. Where's my sort by? Okay, here we say sort by this. No, we could just do a map at. A further map at of framed of hash that's not going to work. It's not going to work. How do we distinguish the very first one of those things? You get what I'm asking? I want to show the very first one in that list of positions. So if I sort those positions, it's not going to have any effect here, right? If I say sort by length here, right, that doesn't have any effect. But what I want to do is I want to highlight the very first of those, right? So I really want to map at indexed here. Yeah. How do I do map at indexed? Look, one grotesque way to do it is to say module I equals 0. if I++ equals 0, framed of SK box, otherwise just SK box of hash. Otherwise just SK box. That's the map at. So I think it's like that. There we go. Okay. I don't quite understand that. Do you understand that? Why those are the correct matches?
I don't think they're correct. Because you won't get the last event this way. The last one clearly is evaluating S.
Yeah, you know, I think I made a mistake here because I think that this sort by position what is that thing there? That's somehow significant. Map at replace. What the hell is that? Oh, that's the default for the first. That's saying if position, no, but why is this, this seems wrong. Well, let's do one thing here. Let's just say, forget all this stuff and let's just say here, map at framed hash background arrow orange for this thing here. I don't think I need that.
Need expert.
What the hell?
Oh, that does seem right when it works.
Why?
Well, it does seem to evaluate the orange boxes. Just some of them are missing.
No, I understand, but is this doing the correct outermost computation? Oh, this is to 8 steps.
Wait, are you?
You know what? This is to 8 steps. Let's do it to 5 steps.
But computation is the same, isn't it? I think it is.
Okay, so I don't understand. So this is saying, why doesn't it show any orange box here?
Well, that's the question.
Oh, I know why. Silly me. There it is. That's the correct thing to do. Right, so that's showing which are the updates that it is doing. Now, why didn't it do on the, why is this showing much less? Oh, this is the comparable one there. Yeah, okay, so this I should do 8 here. Okay, so now.
Yeah, the boxes on the bottom are correct, I think.
for leftmost outermost.
But for the one that it's actually doing.
Well, okay, but is that leftmost outermost? I think it is outermost because that's what it means to have the shortest. That's what it means. Outermost is the shortest sort by length here is going to do the shortest, the highest thing in the tree. So that's the right thing to do, right? See what I'm saying?
Okay.
Okay, so now why is this giving the wrong answer? Why is this showing?
So I didn't hold all, basically. That's the right way of thinking about it.
I'm sorry, what are you saying?
Are you doing hold all?
For what?
For evaluation order?
Hold all. You mean replace all?
No, hold all on S and K.
And then what? That doesn't evaluate
That's
anything.
your evaluation order.
Sorry, I don't understand. Say that again about evaluation order.
So you set attribute hold all to S and K.
Yes.
As far as I understand it, which is why they evaluate before their sub-expressions.
I'd never even thought of that. Are you saying that I could actually do?
I mean, I'm not sure if it's exactly the same thing, but it seems similar.
Wow, that's a very interesting idea.
Well, it's certainly outermost. I'm not sure about leftmost. I guess leftmost should be the default anyway.
I think so. That's a brilliant idea. That's actually very interesting, that point, because that's a parameterization of evaluation order that I hadn't really realized is what. So, I mean, if I were to do that here, let's actually do it. So actually, I won't see anything here because this will it'll just evaluate down to the bottom. But if I did a trace of some kind, would I see it?
Well, I guess. Well, can you limit evaluation depths? I think there is a constant you can
There
use.
is dollar recursion depth, dollar recursion limit, but it's pretty wild. But the other thing to do would be to say echo on the right-hand side. So let's say I did this. Let's say I said SS of, let's get the rules. SS of this colon greater than echo no, that's not going to do it. I don't think it's going to do it. Let's see. KK, that is echo X. And now we say set attributes SS, hold all. So, you know what? There's a question of the head evaluation. Hold all doesn't prevent head evaluation, I don't think. I don't know if there is a hold head.
Let's see. Yeah,
but that's
head
not actually
evaluation.
needed.
That's something I usually think about.
Right, I know. Not needed if one does application-based structure. Okay, I don't think this is going to work as such. Okay, let's not solve that problem. Okay, so now the question is, why did this produce a different answer up here? Why is this giving the wrong answer? Because what it should be doing here okay, there's a sort by here. Look, this should be the first time it comes through. The first SK box do you understand why that's wrong? The first SK box that it encounters, the map at is going to see those I don't know whether that open brace, close brace is important. No, I don't think it is. So this first map at there, let's look at the sort by list here. Okay, so now on the last line, there's a 1. Why the hell didn't it use that? Right, because the first thing that it will get in the map at is that 1 thing, which I would think would be this thing here. Right, that's the first argument. Right. Okay, so why didn't it get that? Okay, map at, if I++ equals 0, then do the frame thing. All right, I don't know whether this is going to be very useful, but we can try this. Well, that's just when it first comes through, right? So now here, we should again just see a bunch of.
Wait a second. Is it evaluating the first argument? Wait, where is the ampersand here? It should be out of if.
It is.
Okay. But the mappet only does one of them.
Does one what? The map at is what's coloring everything, right?
Right, but hold on. There should be 2 maps here. Okay, so one of them is over the steps, which is ordinary map.
Yeah.
Oh, I see. Map, it has a list as a third argument. Is it possible that mappet evaluates it in a different order?
How could it do that? I suppose it's possible. Let me see. Okay, so to check that, what we would do is we would say in the map at, we would say here.
Oh, echo the argument. Hold on.
Echo the hash.
Yeah. And parentheses so that it's out. Yeah.
Oh God. The problem is, oh God, there
Wait,
comes
is
a
it
moment where it's
nesting?
it's already annotated something. How could this be? How could it ever get to this
Wait,
state?
is it map at nesting?
Nesting what?
Okay. Nesting is, well, if you have map at with two indices, is it going to do all of them at once or one at a time?
I understand the question. I think it does them to the original parts, but if the doing of one of them changes the position, no, it's got to do it to the original parts. All right, that's a mystery, but
Actually, it doesn't. Let me send you the code that shows it. So it's sequential.
What is that doing? Wait a minute. That's at part 2.
Yeah, so it does it twice at the part 2. Which means if you replace part 2 with something that it becomes different, and then the next, it affects the next part, it's going to nest.
Yeah.
Instead of doing it independently.
This should become a possible issue. Okay, so just a minute.
It's kind of unavoidable.
If you can come up with an example, I'm going to copy you on this mail. If you can come up with an example that shows this better. Map at works sequentially. So if one operation changes the structure, another operation on the same part will be weird. Do you have an example? Are you about to generate one?
Well, what kind of example want to generate?
Oh, don't worry about it.
I mean, they have to affect the same parts in some way.
Yeah, I understand. Okay, I got to go in a second because I can be up early tomorrow.
Yeah, but it's unavoidable because once you replace a part, it's now different. So you cannot replace a part and its subpart independently.
Okay, well, how do we do this particular thing of saying which one we could mark it first? How do we do this? See what I'm asking?
I don't think does it even do it correctly at all. Not just the first one.
This one here.
Yeah. I mean, it does look reasonable, but I don't understand
No, it
why.
didn't look, oh, there's a K, yes. Well, let's try to understand it. I'll send you this, or you can pick up this notebook, and if you could look at it, that'd be wonderful, and try and understand why it's right, if it's right.
Okay.
Because your point is, by the time it's put in one of those SK boxes, I mean, or it could be that we have to sort this so that it comes up from the bottom, so to speak. So I'm saying,
Yeah,
if we sort the
that
position.
would probably work.
Okay, so that would be a reverse sort by of the length. So, okay, but in a case like this, it doesn't make any difference because it's just the first. But now one thing I want to see, just for fun, is my God. This is just such a freaking incomprehensible thing. How did this Schoenfinkel guy figure this stuff out in 1920? I mean, and we have no idea whether it took him a month or a decade to figure it out. That's the most remarkable thing. We have no idea. Okay, but anyway, just last thoughts on a causal graph for this.
Problem is expression, the duplication.
Explain.
Well, if we have the same subtree, which we deduplicated, and again, if we don't deduplicate it, then one event that referenced it twice for the first time is going to have causal relations to everything that's happening in the subtree, which we want to avoid. But if we avoid it and we deduplicate the expressions, then the same expression might be used in different ways in the same subtree, because that subtree actually exists in two places. So it might be matched in a different way, the stuff above it.
I didn't quite understand that, but I think what you're saying is the the causal dependence, it's because everything is identical. All these things, unlike our hypergraphs, where every atom of space is independent.
Well, the problem here is that you can copy the entire subtrees, and in hypergraphs you can't.
Right.
Well, here's an example. Let's say you have nested S of S, and then your rule says, let's see, S of X pattern goes to something.
But remember, these are proper combinators where it's only S of something or other. The S doesn't appear twice. In these combinators, there is a full copy operation, right? That's saying you can take a piece of the hypergraph, so to speak. Now, is that why you need garbage collection? Is that why these things?
Well, yes, kind of.
Explain.
Well, because you can delete entire subtrees as well in hypergraph's case.
But why is that subtree irrelevant? How does it ever become irrelevant? How does it ever disconnect? Unless there's a K, which there isn't here.
Well, because it doesn't delete any expressions. So if the left-hand side of the rule remains as a subtree and can then continue evolving on its own, the reason it has to do it is because, I mean, we want the system to be confluent, the emulator, which means we need to expect that the combinator rule might get applied before the full duplication process happens. And that means the same sub-expression might be used in different ways. In other words, we cannot delete sub-expression because that sub-expression might be needed elsewhere if it's referenced twice.
Okay.
And if you never delete sub-expression, that means they're going to get disconnected eventually. So basically, all expressions that ever existed is in the final state.
I understand. So, for example, if the combinator got really big and then got small again.
Yeah, that's how you get large disconnected pieces.
Can S ever get smaller? By the way, I am sure that S is universal. It's just a bit more complicated to see it. Anyway, All right, we should wrap it up. I've got to be up early tomorrow. Thank you. And if you have more thoughts on the causal graph, it'd be really helpful. And also, trying to kind of, trying to clean this in various ways. All right, I need to go though, because I got to get up early tomorrow. All right. But you can pick up these files. Obviously, you know where they are. All right.
Yeah.
Thanks. All right. See ya. Okay.
Okay. See you.
Bye. Bye.